Good evening, everyone. Welcome to another session of Network Seminar Series hosted by the Center for Network Intelligence at the ECE and RBCCPS ISC. Today's talk is by Professor Sangeetha Abdu Jyothi, and she will be speaking on understanding internet resilience to planetary scale risk. Professor Sangeetha Abdu Jyothi is an assistant professor at the University of California, Irvine. Her research interests lie at the intersection of networking systems and machine learning. She received her PhD from University of Illinois, Urbana-Champaign in 2019. Before joining UCI, she had a brief stint as a postdoctoral researcher at VMware Research, where she continues as an affiliated researcher. She was selected as a N2 Women Rising Star in Networking and Communications in 2022. Her work won Internet Resilience under Solar Superstorms, won the IETF-IRTF Applied Networking Research Prize in 2022, and received broad media coverage. Before we move on to the talk, we would like to request our audience to subscribe to our Google group. For information on our future talks, you can also visit our website for more details. I'll be pasting the links in the chat box. Please do check. Finally, we request the online audience to keep your microphones on silent for the duration of the talk, except when asking questions. And for questions, you may raise your hand and unmute yourself and ask directly or type them in the chat box. We'll relay your questions. Over to you, Professor Sangeetha.
Thank you for the introduction and thanks for inviting me. Today, I'll be talking about understanding internet resilience to planetary scale risks. Before I delve into today's topic, let me give a quick one-slide overview of research in my group. So at a high level, our current research falls under two broad areas. In the systems and machine learning area, we are working on improving performance and explainability of deep reinforcement learning network controllers. And we also have projects on building systems for efficient machine learning inference and training at the edge. The second key focus in my group is internet resilience, and this includes projects on cloud resilience, wide area network resilience, and internet dependence on other infrastructures like power grids. So today my talk will be touching the two last topics listed here. So the design solutions for internet resilience can be viewed in this two-dimensional space. So on the x-axis, we have the nature of threat, which could be either man-made or natural. And the solutions on the y-axis can be broadly classified into adaptation and mitigation solutions. So where do the current research efforts fall in this space? So network security research primarily target man-made threats, and there are a broad range of mitigation and adaptation solutions. And recently we have this area of research where we are very conscious and trying to improve the carbon footprint of computing. And this can be viewed as a mitigation effort. And here I've listed it under the exogenous or natural threats, but it's indirectly caused by humans. But mostly today, climate change related threats are natural. But here we have a big space where of very large natural threats where we don't have any solutions to adapt on the fly. So this is the area that I have been focusing on recently, where we're looking at large-scale external threats to our infrastructure and how can we adapt our infrastructure to such threats. So first, we'll be looking at internet resilience under solar superstorms. This paper was published at SIGCOMM 2021. So what are the impacts of losing internet connectivity? We know that it can affect our professional and social lives, but for large businesses, the impact can be devastating. The revenue loss per hour for some of the large companies are in tens of millions of dollars. And at the scale of countries, it can be hundreds of millions or billions per day. And it's not just the economic impact. Many other critical infrastructure like healthcare depend on the internet. And if internet fails, it could affect all these other dependent infrastructure as well. And we have had multiple small-scale outages in the past. But what if we have an internet outage lasting weeks or months, spanning the entire globe? Can that even happen? Unfortunately, this is a worst-case scenario that could happen. And this could be due to solar superstorms. So the next once-in-a-100-year disaster after the pandemic could be a solar superstorm that is capable of taking down large parts of the internet. And today, network researchers and operators are mostly overlooking this threat while building and maintaining our infrastructure. So in the first half of this talk, I present a deeper view of this natural disaster and its impact on various internet infrastructure components. There are two types of solar events that are popularly known as solar storms. So they are solar flares and coronal mass ejections. And they both have impact on global infrastructure, but their impact differs widely. So solar flares involve large amounts of emitted energy as electromagnetic radiation. So these are essentially flashes of light, and they can reach the Earth in just 8 minutes. That's the time that light takes to travel from the sun to the Earth. And fortunately, they mostly affect only the upper layers of the atmosphere, and they don't harm any of the terrestrial infrastructure, but they do affect satellite communication. And then we have coronal mass ejections, which involve emission of electrically charged solar matter and the accompanying magnetic field into the space. And these CMEs can take anywhere from 13 hours to 5 days to reach the Earth, depending on the speed at which they are emitted from the sun. And these CMEs are capable of causing significant damages to the terrestrial infrastructure. So CMEs are the focus of this talk, and we'll discuss their impact more closely soon. So both solar flares and CMEs originate near temporary dark spots on the sun's surface, which are called sunspots. And they're caused by changes in concentration of magnetic field flux on the sun's surface. So when the number of sunspots increases, the probability of a solar flare or a CME occurring also increases. Now, how do CMEs affect us? So these magnetized emissions are highly directional. And when the Earth is in the direct path of a CME, it interacts with the Earth's magnetic field, and it produces large electric fields on the Earth's surface through electromagnetic induction. And fortunately, humans are protected from direct impact by the Earth's atmosphere. But these induced electric fields can cause currents called geomagnetically induced currents to flow through long cables that have ground connection that are located far apart on the Earth's surface. So these GIC or geomagnetically induced currents are harmful for infrastructure components that have ground connections that are located far apart on the Earth's surface. So that includes power grids and also internet cables. So what are some of the characteristics of these induced currents? So due to the orientation of the Earth's magnetic field, the higher latitudes are at a significantly higher risk. And it's for the same reason that auroras are more common closer to the poles. And since the impact is caused by interactions with the Earth's magnetic field, the induced currents can affect wide areas and not just and they're not just restricted to the part of the Earth that is facing the sun. And GIC is only induced in cables with ground connections. So you need to be far apart. You need to have connections far apart on this induced field to have these induced currents. And the orientation of the conductor does not matter. Whether it's north, south, or east, west, you are equally likely to have GIC on long conductors. Now, the most important question is, when will a large event that affects the Earth happen next? So solar events are extremely hard to predict, and it's just like earthquakes. Small-scale storms happen all the time, but these extreme large-scale events are very hard to predict. So the largest events on record happened in 1859 and 1921. So the 1859 event is popularly known as the Carrington event. And both these events triggered extensive power outages and caused significant damages to the communication network of that time, which was the telegraph network. And a Carrington scale event actually missed the Earth by just a week in 2012. Now, the estimates for probability of occurrence for such an event, extreme scale event, ranges from 1.6% to 12% per decade. And that's approximately once in 100 years. But that's not all. The risk is not uniform because the solar activity goes through cycles. So here we have the, on the right-hand side, we have the number of sunspots that are seen on the sun's surface per year across nearly 3 centuries. So we can see that the number of sunspots increases and decreases within a certain period. So here, the waxing and waning is in time periods of approximately 11 years. But that's not all. In addition to the 11-year solar cycle, you can see that these big yellow regions indicate another 80 to 100-year cycle called Gleisby cycle. So the peak solar activity differs near the peak versus the trough of the longer 100-year cycle. And this can cause the frequency of CMEs to vary by a factor of 4 across the solar maxima. Now, modern technological advancement happened mostly in the last 3 decades or so, and this coincided with a period of low solar activity. And we never had a very large event in our recent past. So now we are at the beginning of solar cycle 25, and the sun is becoming slightly more active than the past cycle. So we are at the beginning of the next 100-year cycle. And the last moderate scale event actually happened in 1989, and that took down the grid of Quebec state in Canada. After that, we never had a very large event hitting the Earth. So the idea is that a large event could happen soon, and we need to first understand the impact that it could have and be prepared for it. So now, how are the various internet components affected? So localized infrastructure, such as the data centers, can be protected from voltage surges caused by CMEs using transient voltage surge suppressors. So they are relatively inexpensive. So any localized infrastructure is easy to protect. And as I mentioned already, humans or all animals are protected because our atmosphere stops the highly charged particles from reaching the surface. Now, long distance cables constitute the most vulnerable components. So long distance land and submarine cables carry signals in optical fiber. So the fiber in this cable is immune to induced currents because it's just carrying light and not electricity. But these cables also have repeaters at every 50 to 150 kilometers. This is to boost the signal, because otherwise the light signal could it could get weaker as it traverses the cable. So at every about 100 kilometer or so, there is a repeater in very long distance cables, and they're connected in series, and there is a conductor that runs along the length of the cable, which powers these repeaters. So although the fiber is not susceptible, this conductor is susceptible to induced currents. And we currently don't have good failure models for understanding how the submarine cables would respond to large scale failures. And so that's like a big unknown today. Now, looking at other components, internet routers, again, just like data centers, are localized, so they are mostly safe. Now, looking at wireless infrastructure, satellites are mostly deployed in the higher layers of atmosphere and are directly exposed to these solar storms. So they generally have radiation shielding for protection from high energy electrons. So, but however, very strong storms can cause these electrons to penetrate the satellite and destroy or damage its electronic components. And more importantly, it can also cause drag on the satellite, which can lead the satellite to lose the orbit and re-enter the atmosphere and cause them to burn up. So recently, I think it was in February last year, about 40 Starlink satellites were lost to geomagnetic storm when a small scale storm happened. It was because so the lower the altitude the satellite is in, the higher the risk of drag. So these satellites were launched very close to the time the storm hit, and they had not reached their full orbital height, and they were subjected to high drag, and nearly all the satellites in one deployment were lost to a storm. Then cell towers are protected from direct exposure by the atmosphere, so cellular infrastructure is safe. Similarly, personal devices such as laptops, mobile phones, etc., are also safe. But like any electric kind of equipment can be protected by voltage surge suppressors if they are connected to power source. So at the high level, long distance cables and satellites are the most vulnerable components, and other components could suffer from power outages, but they're not directly susceptible to damage. So to understand the impact on end-to-end internet infrastructure, so we looked at a broad range of data sets. So the global submarine cable map, the ITU cable map, which also includes the terrestrial cables. Intertube's data set was US long-haul cables. IXP locations, so internet exchange points are locations where multiple autonomous systems have a presence so that they can peer with each other. So these are very important entities in the end-to-end internet infrastructure. This is where different administrative domains interconnect with each other. DNS root server location. So DNS is like the address book of the internet, and DNS is organized in a hierarchical structure. So the root server are the kind of the root of the hierarchy, and they're the most important part. And then we have the top level domains and so on. So only the root server locations are well known. So we analyze that. And then router locations. So there is CADA dataset, which so this is an organization which has used various internet mapping tools and techniques to derive the router addresses and locations across the globe. It's not a complete data set. So they use techniques like trace routes to get information. So we are limited by how many vantage points we have, etc. So it's an incomplete data set, but this is the largest data set that we have today. And then next we look at how these infrastructure components are distributed across the globe. So we know that higher latitudes are more vulnerable to induced currents, particularly latitudes above 40-degree threshold. So we evaluate the distribution of internet infrastructure components in this range. So here we have the probability density function across various latitudes plotted on the x-axis. So we look at the distribution of population and submarine cable endpoints. So here we see that the population is mostly concentrated below 40-degree north, but we have a high concentration of submarine cable endpoints above 40-degree north. And this is not just for submarine cables. We looked at various other internet infrastructure components. So here we have internet routers, IXPs, DNS, root servers, etc. Across various latitudes. So on the x-axis, we have the latitude threshold, and on the y-axis, we have the percentage above a particular threshold. So here, what this means is that at 40-degree, above 40-degree latitude, this could be above 40 north or minus 40 south, we have about 18% or 16% of the population, but in the same region, we have about 35 to 45% of most of the internet infrastructure components. And this is the more vulnerable region. And although most of the user population is below this in the less vulnerable region, the infrastructure components are actually concentrated in the more vulnerable regions. Next, we look at the cable length distribution. So again, as we already saw, long distance cables are at the highest risk. So here on the x-axis, so we plot the length distribution of land and submarine cables. And here on the x-axis, we have the length in kilometers, and note that this is log scale. And this is the CDF. So, so the cables have repeaters only if they are longer than 150 kilometers. So this is the length threshold below which the cables don't need a repeater. And we see that a large fraction, more than 70% of the cables are really short on the land. But we see that only a very small fraction, 20% of submarine cables are shorter than this threshold. So most of them are very long and need the repeaters, so they are vulnerable. So submarine cables are more vulnerable than land cables when it comes to this geomagnetic impact. So we also look at country level analysis. Now, if we look at the US, we can see that on the northeast, most of the cables go from, on the eastern side, most of the cables go from northeast to UK or Spain. So because, and this threshold is above the 40-degree north threshold. So if there is a solar storm, if there's an extreme case event, then US could potentially lose connectivity to Europe. And there are no cables from, so if you look at the map, like the southern tip of Florida is below the 40-degree threshold, and there are no cables that go from southern part of US to southern part of Europe. And that's because this is much longer and leads to higher latency. So from a performance perspective, this is not a very useful place to install cables. But from a resilience point of view, having all the cables concentrated in the northeastern region is probably not the best for resilience under extreme case events. Now, if you look, and then if you look at South America, there are only a couple of cables that go from Brazil to southern part of Europe, and they are actually less vulnerable. And because these cables are in fact shorter than the US to Europe cables, and they are also closer to equator, so they are less vulnerable on both fronts. But most of the traffic from South America to Europe actually go from South America to North America and then to Europe today. There is very limited cable connectivity in this region. Now, if you look at Asia, Singapore is actually a hub, and it has relatively shorter connections to most of the neighboring countries, and it's located much closer to the equator. So overall, Asia has a higher chance of retaining connectivity, with Singapore acting as a hub between the neighboring countries. So that's kind of a high-level analysis at a country level. Now, if we look at data centers, this is a distribution of public data centers across the globe. So here, red shows a higher density, followed by orange, and then finally blue. And we observe that data centers are concentrated again in highly vulnerable higher latitudes. And this observation also holds for hyperscale providers like Google, Facebook, Amazon, etc. And even if they don't suffer direct damages, access to these data centers can be affected if there are large-scale outages. And there are some other observations. If we look at DNS root servers, they're actually very highly distributed with good presence across the globe and hence not vulnerable. And then we also looked at autonomous systems spread in the vulnerable regions. And a large fraction of ASS actually have a presence in vulnerable regions. And but the vast majority of ASS have a small spread. There are very few large ASS. So these are some of the high-level observations regarding the solar storm risks. So before I move on to the second part of the talk, are there any questions on this part?
And one question, so what percentage of internet traffic goes through undersea cables currently?
So the exact percentage is not known, but a large fraction of about 99% of the intercontinental traffic actually goes through that, and it is in several TBPS range. But the exact split between land and ocean cables are not known.
Mm-hmm.
But
and
okay.
Sorry, go ahead.
No, but if we look, but between sorry. Yeah, but between, say, North and South America to Eurasia, there is no other option than going over the submarine cables.
And are they also susceptible to large-scale undersea currents, which is far more disruptive damage to the cables than repeaters?
No, so these cables are typically buried under the ground, not very deep, but they actually dig holes and then bury the cable. So the currents itself don't affect them, but they are susceptible to damage from like ship anchors. And also recently Tonga lost their cable because there was an underwater volcanic eruption. And during earthquake in Japan, the sea floor shifted and multiple cables had gotten damaged in the past. So they are vulnerable to various other natural disasters, but not currents because they are buried underground.
Okay, thank you.
Okay. So next, we look at a second category of threats to the internet, which arises from dependence on other infrastructure. So among critical infrastructures, power grids and communication infrastructure are identified as uniquely critical because every other infrastructure depends on them. And they're also interdependent on each other. So internet routers and these long distance cables and almost every component that forms the back end of the internet depends on power. And the power grid also depends on communication for between the substations for deciding how much a supply should be increased or decreased by, or various control signals are transmitted between various elements of the power grid infrastructure and so on. So the power grid infrastructure and the internet and the communication infrastructure are both very important and they are interdependent. And they're not just isolated by themselves. They also depend on like the water infrastructure. So today data centers use water for cooling. Power grid also uses water for cooling. And then both depend on transportation infrastructure and so on. So if we look at critical infrastructures in our society, they are each independently important. And at the same time, they are also very tightly dependent on many of the other critical infrastructures. And this forms a kind of very interdependent backend for our society. And it's also unfortunately prone to cascading failures. So before we delve into the failures part, let's see how the power grid infrastructure is organized. So, as we all know, power grid infrastructure interconnects the sources of power generation with the consumers, and it's composed of power stations, substations, low and high voltage transmission lines, and so on. And typically, today's power grids, they don't have energy storage because that's very expensive. So the power generation is adjusted to match the demand. So, today most grids are wide area synchronous grids. And what does that mean? These are large grids operating at synchronized frequency, and this is for various economic benefits. So it allows pooling of reserve capacity across multiple grids, and it reduces the need for like the peak generation capacity and so on. So due to various benefits, grids are moving towards these wide area synchronous grids. And if we look at the world map today, these are the prominent wide area synchronous grids. So India has a single grid today. Previously, we had a northern grid, southern grid, eastern grid, and so on. In the last decade, they were unified into a single national grid. If you look at the US, so there are three main grids in the continental, in North America, the Eastern interconnection, the Western interconnection, the Texas grid, and there is also Quebec grid. Alaska has a separate grid. Europe has a single Europe continental grid, but UK and Ireland, etc., out of it. But it also interconnects with a few countries in North Africa, and then we have the UPS grid, which interconnects the previous Soviet countries, and then even in Africa, there's a South African power pool, and there's a West African power pool. Some countries in North connect with Europe. Australia has 3 grids. Even in South America, there are many large grids. So across the globe, grids are moving towards these wide area synchronous grids because it provides a lot of cost benefits. Now, these grids are typically designed for N-1 security. And what does that mean? It means that if a single component fails, the grid is guaranteed to continue its operation without affecting electric supply and without causing any failures. And we know how to design grids for N-K security. What if K elements fail at the same time? But it's very difficult to and very expensive to give N-1, N-K security. So although we know the solution, they're not employed today. So what does this mean? If more than one component fails within a very short time, these wide area synchronous grids can be susceptible to cascading failures that can bring down the entire grid. So if we had a smaller grid, only a small region would go down. Now that we have a very large grid, these cascading failures could bring down the grid across a large region. And this is not a theoretical possibility. This has happened many, many times in real life. So the most recent one was actually last week when the Brazil grid went down. So the cause is still under investigation, but except for one state, all states in Brazil had their power grid down, at least a part of the grid affected last week. And it took about 7 hours to bring the grid back up. And this in turn affected the communication, transportation, many trains were stopped and so on. So this has kind of impact on all the other infrastructures. In India, back in 2012, at that point when we had 4 different grids, the northern grid had failed, affecting power supply to more than 600 million people. And it took nearly more than 24 hours to bring that grid up. New York had a large outage in 2003, where again, millions of people, more than 50 million people were affected. And it's very interesting that these failures are not caused by very large scale kind of component failure. In the case of Brazil, last week's failure, the report is not out yet, but a single cable failed and it caused cascading failure across the large country. And even in India in 2012, overloading of a single link and some misoperation of its protection system caused this cascading failure across the whole grid. And in the 2003 US outage, it was some software bug in the alarm system somewhere in Ohio. And again, the entire eastern part of the US, the power grid was taken down. And these are just 3 examples. There are many, many more. In 2019, Argentina had a 14-hour outage that extended across Paraguay, Uruguay, etc., affecting again close to 50 million people. And Wikipedia actually has a page on large-scale power outages. So, and there's also a lot of work in the power grid community on modeling these cascading failures in the power grid infrastructure. So this is a kind of known problem, and it does happen now and then, and it has been happening for some time now. So, here we look at how the internet was affected. So this is the Brazil map. So there is one state on top which was not affected. All the other states in Brazil had some level of power outage last week, and in fact 27% of the total load was affected. And this is the internet failure map from IODA, which is like outage detection platform run at Georgia Tech. So this is a snapshot from there. When the grid was affected, it also caused large-scale internet outage across the country, affecting multiple ASS within Brazil. So the power grid failures can indirectly cause internet failures. Now, and this has been happening for some time. So, but why study it in more detail now? So today we are facing increasing threats. So as we see in the news today, we are seeing an increasing frequency and intensity of extreme weather events due to climate change. And there's also increasing threat of solar storms due to a strengthening solar cycle. And as I said, long distance power cables are also vulnerable to failures. And there are also various targeted attacks, like electromagnetic pulse attacks that could be used to bring down the grid. And especially in the US, there have been in the recent times, multiple people attacking substations, etc. So grid is like a target for attack because it can bring down the entire society if the power grid fails. Also, at the same time, I showed large-scale grids across the globe. Most of these large-scale synchronizations happened in the past decade or two. So as the grids are growing larger and larger, the threats are also increasing. So we will see more and more large-scale outages as things get worse. And there are studies that already show that as the temperature rises, the failure rate of various components in the power grid infrastructure increases. So the chances of cascading failures can also increase. So, so to understand the impact of power grid failures on the internet, I looked at the overlap between these infrastructures. So currently we have work on internet failure analysis alone and also power grid failure alone. But understanding the interdependence and studying how the joint failures would happen is like a very difficult problem. So this is just a first step towards that. So here we have the 43 wide area synchronous grids on the x-axis. And this is the internet exchange point distribution across these wide area synchronous grids. So here on the y1 axis, we have the total IXPs. So we have about 1,100 IXPs across the globe in a publicly available data set. And this is the fraction of IXPs. So, so about 88% of IXPs are located in some wide area synchronous grid. And if we look carefully, we can see that nearly 50% of the IXPs are in fact located in close to five or six wide area synchronous grids. And if we look at routers, so again here we have the wide area synchronous grids on the x-axis, and the routers on in millions in the y1 axis, and this is the fraction. So here we can see that so this is over 50 million routers for which we know the geolocation. This is obtained from the CAIDA dataset, which is publicly available. And here more than half of the routers are in fact located on just 3 wide area synchronous grids. So the internet infrastructure distribution is very skewed. And if these grids are affected, it could in turn affect the internet connectivity significantly. And this is a more detailed look. So here we have the IXP, again, internet exchange point distribution, but across the top 15 wide area synchronous grids, sorted based on the number of internet users. So we have India, this is one of the Chinese grid, European grid, North American Eastern interconnection. This is a West African power pool, Japanese grid. This is the Soviet grid, and so on. So here what we see is that the European grid, so in total we have about 1,100 IXPs, internet exchange points. And more than 200 out of 1,000, that is 1,100, which is nearly 1/5 of the IXPs are located just on a single grid. And if the European grid is affected, this could affect all the IXPs on that in that grid. And even the next largest, which is the North American Eastern Interconnection, has only half of the IXPs that the European grid has. So this is just like a brief peek into results. If you're more interested in this line of work, you can take a look at the paper. I've just cherry-picked a few results here, but I've looked at more detailed analysis on various internet infrastructure components and how they overlap with the wide area grids. And this is another very interesting aspect, the cloud provider availability zones and how they overlap with these grids. So if you look at AWS, Amazon's web service, they offer availability zones. So these are fault isolated locations within a region. So if you want to run an application and you want it to be fault tolerant, you can place replicas across more than one availability zone. And then AWS guarantees that the application will be available even if one of them fails. So they are fault isolated. So the Amazon's guarantees that they won't fail at the same time. And AWS has 27 regions. So these are just various regions across the globe. And within each region, they have multiple availability zones, which are these fault isolated regions. So here are here's a distribution across the top 15 grids. So if we look at India, for example, India has a single AWS region, but 3 availability zones. Europe has 3 regions and 9 availability zones, and so on. But the thing is that now if the grid is affected, although from the AWS perspective, the availability zone data centers are independent, if the grid where these data centers are located are affected, they might all be unreachable at the same time. So when this power grid dependency is taken into account, the number of isolated zones decreases from 87 to 19. If you really want if you really want to place your replicas in 2 zones which are unaffected by failures, then you probably want to place them in 2 different power grids. Only then they will be actually fault isolated. So this is an interesting observation, and this shows that our cloud providers and various internet infrastructure kind of entities are not taking into account the power grid dependence when they think about fault tolerance. So these are some of the other high-level takeaways. I've just shown a few results from that work. So what we see is that nearly 65% of the internet infrastructure components are concentrated in fewer than 10 wide area synchronous grid regions. And North American Eastern Interconnection and the European Continental Grid host the largest fraction of internet infrastructure components. And availability zones of cloud providers actually do not take into account the power grid dependence. Another interesting thing is regarding this solar storm resilience. So what we looked at earlier was the distribution of internet infrastructure components above the threshold. But now if we look at the grid, for example, California is below the 40-degree threshold, but the Western interconnection that powers California has some part of the grid that's above the threshold. So if there are failures above the threshold and it cascades, then regions below the 40-degree threshold could also be affected. So if we actually look at power grid dependence, a larger fraction of the internet infrastructure could be at risk. So this is again only a first step towards this direction. Understanding the power grid and internet interdependence is like a very complex subject. There is a lot of work on understanding how communication network failures affect the grid, but how the grid failures affect the communication infrastructure is not very well understood. So this was a quick overview. Next, I have some high-level open research directions in this in the space of internet resilience. So before I delve into that, any questions on it now? Okay, so let me get moving. So so the two works that I just discussed takes the first step towards understanding the risk, and there's a lot of open questions in this space. So first, we know that the internet is composed of multiple layers. First, we have the physical infrastructure, then we have the IP links, then we have autonomous system level links, then we also have the other infrastructure components like the DNS infrastructure and so on. So if a cable fails, and many of these natural threats that we are talking about, extreme weather events caused by climate change or even solar storm impact, they actually affect the physical infrastructure. Now, how does the failure of an underlying physical infrastructure component affect the higher layers? And we don't have all the pieces to answer that question well, right, today. So, so today, internet resilience analysis is hindered by missing or incomplete data and tools on various fronts. So first is internet physical infrastructure maps. So, so if we look at CADA and various other kind of data sets that are available today, they're mostly focused on Europe and North America. So if we look at CADA's router data set, for example, North American Eastern region that we saw has nearly 1/3 the users of Indian region. If we look at the raw number of users, but the number of routers that we have in that region is nearly 10 times of the routers that are detected in India. And because we have good internet connectivity and also a large population of users, I don't think it is because we don't have routers. It's just that they are not mapped today. If we have better mapping and also kind of better data set collection in this region, we can have a much richer data set, and this will enable much better studies on like higher layers of the infrastructure. And this is not just a case with India. Most of other Asian, South American and African countries, we don't have much data on the internet infrastructure. So that's clearly a big gap today. And then another thing is like what I just discussed, the cross-layer mapping. If a cable fails, what IP links will fail? What AS links will fail? How will the BGP paths change? So it will failure at one layer will result in cascading failures across multiple layers. And in order to understand that well, we need to know what links go on each cable. How will a cable failure affect higher layer links and so on? So, so that's again another kind of area where we have very limited solutions. Another thing is like we know there are like packet simulators like NS3 where we can do low-level simulations, but at a much smaller scale. Now here we are talking about end-to-end analysis at internet scale, and today we don't have good frameworks where we can study how, you know, across tens of thousands of ASs, how BGP path changes would kind of evolve. We can't simulate that well, and we don't even know the full map yet. So how can we simulate, you know, cable failure, and then if we have a complete map for the entire infrastructure, how would that translate to changes across the layers? So we need more efficient frameworks for scalable end-to-end analysis. So currently my group is working on some parts of this, but this is like a very big open research area where, you know, it will be great to have more people looking at it. And then on the other side is how do we improve the long-term resilience of the internet infrastructure? It's like very important for everybody across the globe. So for example, this could involve adding new cables in locations, even if it's not optimal for performance, like latency performance, maybe we need it for better resilience. Another interesting direction could be design of new interdomain routing protocols, especially in the context of like CMEs, where, you know, large scale outages could happen and a lot of paths might be down. Then BGP's rule of selecting only one path might be very limiting. So can we have more multi-path solutions across the internet? And then in the case of many natural disasters, we often have lead time. For example, CMEs, we could have 13 hours to 5 days. For hurricanes, we very often have lead time. So in some cases, we might have some preparation time. So how do we use that well so that we improve the overall connectivity and resilience during the event? So that's an interesting topic to look at. And then again, large scale failure analysis. Most of the failure analysis that we do, even at data center scale or application scale, is like, what if a link fails, or what if a limited set of components fail? Now we are talking about failure scenarios where large fraction of the internet might be affected. So how do we design the right kind of tests for this setting? How do we build the right failure models and so on? So this is another thing where there is a lot more research to be done. So to summarize, so the internet has not been stress tested under extreme case failure scenarios. And today we are facing increasing threats to the internet infrastructure from both extreme case weather events, as well as increasing likelihood of extreme solar storms. Now, we saw that the internet infrastructure components are heavily skewed, and this could increase the vulnerability of the end-to-end infrastructure. So we need more work on better understanding as well as improving the resilience of the global internet infrastructure. With that, I'll stop, and I'm happy to take questions now. Thank you.
Thank you, Professor Sangeetha. If there are questions, please ask. I have one question: that are there any potential solutions to this yet?
This, as in, can you can expand? Like, you mean large scale threats?
I guess we lost Ankita, and then her network connection.
Hello?
got disrupted.
Oh, yeah, sorry.
So yeah, potential. I'm curious about the direction or the potential solution to this large scale threats, actually.
Oh, yeah. So as I mentioned, so today I don't think we have any good solutions, end-to-end solutions yet for end-to-end solutions for large-scale threats. And there are a lot of missing pieces towards that. One is that we don't have a good understanding of the infrastructure itself. We need better mapping and better kind of end-to-end understanding of the infrastructure. So that's one thing. And then there are also, at the various layers, how can we design more resilient solutions? So internet is built to be fully distributed and resilient in many ways. But unfortunately, what we are seeing is like there's concentration of power on many fronts. Like the infrastructure is being concentrated in with certain companies, certain regions, and then we have even the newly laid infrastructure components are being kind of driven purely by business constraints and not based on kind of global good as a criteria. So but various internet infrastructure components do have inherent kind of resilience capabilities to some extent. So if a few parts fail, BGP can easily find an alternate path, and the communication can continue. But if we have very large scale failures, these protocols may not be able to adapt well, and there could be a lot of churn in the back end. So yeah, at that scale, we don't know how the infrastructure would respond, and we don't have very good solutions yet. So that's like a good topic for students to work on.
Correct.
I see a hand. Please go ahead.
Yeah. So, as I understand from your talk, there are no internet scale simulations done to analyze these large scale disruptions, whatever be the reason. Is that correct thing to take away?
Yeah, yeah.
So, if someone were to do this, what would be the simulator? Assuming again the data is available, I'll ask the related question on the data availability. But assuming you know the topology or the configuration of all the links, then what kind of simulator would be required for doing this end-to-end study?
Yeah, so first thing we would need, like the simulator would need to take into account like the cross-layer dependencies. So so if we just look at the physical cable map, we can easily do the network graph analysis, but that's not enough, right? Because the physical cable graph has like a IP level map on top of it, and then there is an AS level map that is built on top of that, and then the DNS. In order to reach the DNS infrastructure, you might use certain paths that are determined by the AS level paths. So it's a very complex, interdependent, multi-layer kind of environment. So so the simulator would ideally need to take into account these multiple layers and their dependencies.
So a simulator like NS3, will it do the job?
No, so NS3 can simulate all the protocols, but the thing is, since it's like packet level simulator, it's very slow. Even if you have like 100 nodes, it doesn't like it takes it could take hours to kind of simulate the network if we need kind of fine grained analysis. So it's just not scalable.
Okay, so you need something which is more specialized towards checking the reachability
Yes.
at multiple layers. Okay, and the other related question is this CAIDA data set, it's not representative enough. Is that the thing? So having this Atlas right probes, does it not help build this kind of topology?
Yeah, so the thing is, CAIDA has multiple BGP kind of it takes data from multiple BGP looking glass servers and so on, and they have their own kind of long running trace route measurements going on, with which they derive the trace route, they extract the links and then the geolocation and so on. It's a very complex kind of process. So today, you're right, RIPE Atlas has about 10 to 15,000 probes that are more geographically distributed. And we can get the data, but the thing is, we don't have the full end-to-end processing pipeline yet to extract full data across the across the globe. And again, geolocation, etc., uses a various combination of techniques. So I'm not sure to what extent CAIDA's processing pipeline is available today, publicly available that we can use. So, so I've looked at the data set, and that's very clearly skewed. The North America and Europe is very highly, very well represented, and for the rest of the globe, the information available is much less. But again, I've not looked at how well distributed RIPE probes are in India, for example. So again, it will depend on how many vantage points we have and how many trace route measurements we can run from there. So that will determine how well of a map we can derive from that. Yeah, so this has not been done before. So if anybody is looking or for a topic and this is of interest, this is something worth doing.
Okay. So I guess the BGP broadcast or the BGP peering information will give you the AS level information, right? So only the geolocation is a problem in this.
No, again, BGP, the thing is, since BGP only propagates one path, so if you look from a vantage point in, say in US, the path that you will see to India is just one path. But if you have a vantage point located much more closer here within an AS, you can see all the paths that AS receives from its neighbors. So the farther the vantage point is from a region, the less kind of zoomed in version of that region you have.
Okay, so and is it possible for non-service providers to build this kind of eligibility maps, like all possible paths to a single IP destination or subnet
so
that is advertised?
So trace routes is easy, right? Because the right probes are there. So if you have multiple probes, then you can run trace routes from anywhere. And like educational institutions can get together and then have multiple trace route measurements. But for BGP information, you need to peer with the AS. Like they need to be willing to give it to you. So that is more hard to get.
Okay. So like one insight that like I can share is that in India, typically the service providers are not sharing enough information with academic world as well as the open source community. So whereas many of the Western universities have had collaborations with service providers, IXPs as well as the service providers, so that way a lot has been analyzed and written about.
Yeah, but I think is it just because of business reasons that they are not open to it?
I can't comment on that. I don't know.
Yeah, no, because there was a paper on a European IXP, and they just looked at a single IXP, and they found more peering locations there than what was known in public across the globe. They found more peering locations in that one IXP. So I would guess that if we had a more closer look at Indian internet exchange points or any one AS, if we can manage to get that, it will be like a treasure trove of information.
Yeah, this is an interesting point. Actually, we should try to reach out to the Nixie who runs the IXP in India.
Okay, if there are no more questions, we can close this session.
Yeah, thanks a lot for having me. This is very nice.
Yeah, thank you, Professor Sangeetha, for an informative talk.